Okay guys, Assalamualaikum, good day. So now we go for the chapter 1. So the introduction and basic concept of thermodynamic. This is the objective, and this is the thermodynamic definition, whereby the thermodynamic is the science of energy. We are trying to look all the energy involved in mechanical engineering. And what is energy? The ability to cause changes. Okay. Basically, in thermodynamic, if we talk about energy, we are looking at the energy conservation principle. And we know that the principle said that the energy cannot be destroyed, nor can be created. But energy can be transferred or can be changed into the other form. So this is the first law of thermodynamic. It's basically the conservation of energy principle. The second law of thermodynamic always show the processes in terms of the quality and direction, the quality and also the theoretical limit. And also we look at the efficiency. Right? The quality can be put into the term of the efficiency in the second law of thermodynamic. In our case, we are looking at the thermodynamic as using the macroscopic approach, which is more suitable for the mechanical engineers rather than the statistical thermodynamic approach, which are using the macroscopic aspect of the chemical content or the chemical equation for the working fluid. This is some of the example of the areas of the application of thermodynamic: power plant, ships, boats, refrigerator, okay, air conditioning system or the heating system in the house, and also for propulsion in aircraft. Now we go for the dimension and units. What are dimension? Basically, the dimension is MLT, mass, length, and time. This is called dimension. And the unit for mass is kilogram, length is meter, and time is second. So in the dimension, we have the primary and the fundamental, or also known as the fundamental dimension, which is MLT. And we also have the secondary dimension or direct dimension. Basically, we look in terms of the unit that we have. Right? For example, if we have kilogram, this is fundamental. If we have Newton, that is derived. Kilowatt is derived, and etc. In our approach, in our case, we are going to look the metric system as far as the unit is concerned. So this is all the dimension and unit involved. And this is the prefix that we can use to represent a very large or very small figures or numbers that involve in thermodynamic. Okay, usually we are using the deci, centi, milli, micro for decrement in values. But for bigger values, we usually use kilo, mega, giga, tera, and etc. So these are some of the units that we have. This is the English unit, or is also known as the imperial unit. And this is the unit conversion. Okay, this is called unit conversion. So for example, if we have force equal to M times A or force equal to M times G, so when M times A, we get kilogram meter per second squared, and it's also known as Newton. So this is basically the fundamental or the primary unit, and this Newton is the derived unit. In order to change all the unit, what we must have is the conversion of those units that we want to convert. For example, this is the example of conversion unit. This is also known as the conversion unit. So our first equation right here is W equal to M times G. also known as a force, but this W usually subjected to the gravitational type of force. Okay, example of forces in SI and also in the imperial unit, English unit. So this is the second one, is we look into in terms of the dimensional homogeneity. Okay, so for example, if you want to add up certain figures or certain numbers, we must make sure that we have the homogeneity of the unit. For example, that we can look in terms of the unit for energy. You know that the energy consists of three main elements. One is the internal energy, and then we have the kinetic energy, and we have the potential energy. Okay, usually we can look at the internal energy we use as a kilojoule over kilogram, and then the KE we are using the formula as the V squared over 2, and the PE we are using in terms of G times Z. Okay, so if we look this U, or usually the internal energy, we are getting from the properties table. As far as the water and R134 is concerned, we are getting this from table. Okay, table of properties, whether we are using water or we are using R134A. So always the unit is given as kilojoule over kilogram. But as for the KE, we are getting from the derivation or the calculation of velocity divided by 2, kinetic energy. And when we look at the energy or the unit analysis, we are finding that this is in terms of meter over second for velocity. Then when we square it, we are getting this is as meter squared over second squared. And then we try to get the energy as what we have right here in terms of kilojoule over kilogram. So what we have to do, we have to look before we sum up this total of energy in terms of U, KE and PE, we must make sure that the unit is the same as in internal energy, which is kilojoule over kilogram. So what we do right here is we multiply kilogram over kilogram. Then we can rewrite the unit as meter over second squared multiplied by kilogram, and this is must also multiply as the 1 over kilogram. Okay, and we know that this is mass time acceleration. So this will give us the unit of Newton. Okay, and we have one more meter right here. So this is meter. So what we have right here is Newton meter over kilogram, and this is equivalent to joule over kilogram. So when we analyze the KE will give us joule over kilogram, whereas from the table we are getting kilojoule per kilogram. So we cannot sum up this formula as the raw numbers that we have. We could not just add up in U, so we have to convert this unit to kilojoule over kilogram. So what we do, we multiply this by K, and we know that 1K is equal to 1000. Then now we have kilojoule over kilogram, but we must divide this value by 1000. So then only we have in terms of kilojoule over kilogram. Under one condition, we must multiply this by 1000, divided by this by 1000. Okay, Same goes for the PE. As far as the PE is concerned, we have the formula for PE is equal to G times Z. What is the unit for G? G is a meter over second squared. What is M? What is Z? Z is in meter. So if you can look here, we are getting the same thing. Okay, this is the as meter squared over second squared. So by using the same method right here, what we have done to the KE, then we must divided this joule over kilogram as to convert as kilojoule over kilogram. Okay, so in order to have this as in kilojoule over kilogram, then we must divide this by 1000. So this is called the unit homogeneity. Okay, and also how to convert all the unit that be involved right here, right? So we must get the proper conversion of the unit. If we don't have the conversion of the unit, then we cannot convert from one unit to another unit. For example, let's say we have pressure. Okay, what is pressure? Basically, pressure is equal to force divided by area. Force divided by area. And what is the unit for force? Is Newton. What is the unit of area? The unit of area is meter squared. Okay, so we know that Newton over meter squared is also known as Pascal. Okay, as Pascal. So we want to convert from Pascal to another unit, we must have conversion unit. For example, that if you want to convert Pascal to kilopascal, then we have to multiply this by K over 1000. So this is called the conversion, or in this case, it's the prefix we use. So right here, then we have kPa, meaning that this 1000 we must put right here. Okay, so this is an example how we convert the unit involved. So it's very important for us to look in terms of the dimensional homogeneity, and sometimes the unit also will give us the formula that we should use to get a certain parameter. Okay, for example, if we want to look in terms of the density, okay, let's say we have density. What is the unit of density? The unit of density is the unit of density is kilogram over meter cube. So if we look right here, the unit is kilogram per meter cube. What is kilogram? The fundamental of kilogram is mass, and the meter cube is volume. So this is the formula how to get the density. Same goes for the specific volume. What is the unit of specific volume? We know that this is meter cube over kilogram. So you can write the formula for this specific volume as volume divided by mass. So this is the example whereby we use the unit to get the formula for a certain parameter. Okay. Now we go to the terminologies used in thermodynamic. We have system. What is a system? A system is a matter or a quantity of region chosen for study. And for our case, usually the system is called as the thermodynamic system. Okay, it's called as the thermodynamic system. And in thermodynamic system, we are going to learn three types of system. Okay, whereby the first one, we are looking at water, H2O. And then we are going to learn about R134A. And also we are going to look at the ideal gas. So this we are going to learn three types of thermodynamic system in our scope. And then what is surrounding? The surrounding is anything outside of the system. And boundary is an imaginary line that we try to sketch to separate between the system and the surrounding. And we have two types of boundary. One is fixed, one is movable, and it can be considered as a closed and open system or control volume system. Okay, the open system also known as control volume system. And this boundary or this system boundary can be imaginary or can be a real physical type of boundary. So this is an example of the boundary, system and surrounding. So this is a closed system. Okay, and is subjected to a heating process. So this is the final state of the heating process. So you see, we can have the boundary as an imaginary boundary, or we can have physical boundary, and the boundary can move. Okay, and in this case, this is a closed system, whereby in closed system we don't have mass interaction, but we have energy interaction. Okay, this is an open system or control volume system. This is an example of a nozzle, whereby this boundary is being imagined or being assumed as an imaginary boundary for inlet and outlet. But as far as the side of this boundary is a real boundary, basically is the casing of the construction of this nozzle itself. This is again another example of open system. We have the charging process. Example of the open system, whereby we have a water heater. We have water in, cold water in, and cold water out.